Lesson 7.1, Solving Systems of Two Equations. This lesson will be a review of things we've talked about in the past, review the different types of algebraic methods to solve systems, we'll review the different types of solutions we can end up with. We'll also go through solving a system that does not just involve linear equations. So what we'll review in this lesson is the two algebraic methods, substitution and elimination. Elimination, also called linear combinations. We'll discuss the graphical method and then go through one or two application problems at the end incorporating these main ideas. When referring to the solution of a system, that is referring to an XY ordered pair that is a solution to each equation in the system. Okay, we can have one solution, infinitely many solutions, or no solution. We'll go through that a little more in depth when we go through some examples. First example, we want to solve the system using the substitution method. We use the substitution method if we have a variable with a leading coefficient of 1 or -1, which in this case, if we look at the first equation, our y variable has a coefficient of -1. So the first thing I'm going to do is to solve that equation to get y isolated by itself. The new equation we end up with is y equals 2x minus 10. Once we have this variable isolated by itself, now we're going to use the substitution part of this method. We're going to substitute 2x minus 10 in for y in our other equation. Because in our equation right now we have two unknown values. If we substitute in this expression, then we'll have one unknown value, x. Now we end up with 6x plus 4 times the quantity, 2x minus 10, equal to 1. Now we just have to go through and use algebra to solve for the value of x. To solve for x, the first thing we would do is distribute this 4 through to each term. Thus we get 6x plus 8x minus 40 equal to 1. We can combine like terms on the left side of the equation. 6x plus 8x gets us 14x. We would add the 40 to the other side to get 41. Now the last step to get x isolated by itself is to divide by 14. So we get x equals 41 over 14. Now once we have the x coordinate, we need to substitute this value of 41 over 14 in for x in this equation up here so that we can solve for y. Now once we substitute in 41 over 14, we just have to simplify this expression. We multiply this through and simplify, we get 41 over 7 minus 10, get a common denominator, and once we simplify that fraction, we get negative 29 over 7. So the solution to this system is the ordered pair 41 over 14, negative 29 over 7. In the next example, we want to solve a nonlinear system. So we have y equals x squared plus 6x, a quadratic function, and y equals 8x, a linear function. What we're going to do in this case is set each of these expressions equal to each other. Since both of these are in y equals, essentially we're using the substitution method. We're going to substitute 8x in for y into our first equation. Now we have 8x equal to x squared plus 6x. If we want to solve a quadratic equation, we want to set it equal to 0, so we would subtract 8x to the other side of the equation. Now we would have 0 equal to x squared minus 2x. Take out the common factor of x, which leaves us with 0 equals x times the quantity x minus 2. Now once we have it in factored form, we use the zero product property, set each factor equal to 0. Thus we get x equals 0 and x equals 2. Now we have to plug each of these x values back into one of the original equation. Does not matter which equation we plug it into to find the corresponding y values. When we plug in 0 for x, we get 0 for y. When we plug in 2 for x, we get 16 for y. So these are the two ordered pairs, 0, 0, 2, 16, that are the solutions to the system. If we would graph both of these equations on the same coordinate plane, that means they would intersect at 2 points, which are the two ordered pairs we found. In the next example, we're going to use the elimination method to solve this system. We have 3x plus 2y equals 12 and 4x minus 3y equals 33. First thing you should do when using elimination is to make sure you have like terms lined up vertically. Now what you're trying to look for are any variables, either x or y, that are going to be easy to eliminate, where one is positive, the other is negative, and they have the same absolute value for their coefficient. So in this case, I'm going to eliminate the y variable because I see one's positive and one's negative, and I can multiply each of these equations by some constant so that I get those absolute values to be the same. I'm going to multiply the first equation by 3, and the second equation I'm going to multiply by 2, because then the absolute values are going to be 6, and when we add those together where one's positive, one's negative, they'll simplify out. So my new equation is 9x plus 6y equals 36, 8x minus 6y equals 66. We need to add these two equations together and then solve for x. When we add those two equations together, we get 17x equal to 102. To get x by itself, we would divide by 17. 102 divided by 17 is 6. Now we need to take this value of x, substitute 6 into either of these equations, does not matter. Substitute 6 in for the x value to solve for the y value. I chose to use the first equation. You could have used the second equation. So I have 3 times 6 plus 2y equal to 12. So I get 18 plus 2y equals 12. To get y by itself, first I have to subtract 18 to the other side. We get 2y equals negative 6. Thus divide by 2, and we get y equals negative 3. So the solution to this system would be the xy ordered pair, 6, negative 3. In this example, we want to solve the system using whichever method is going to be easiest. In this case, I'm going to choose to use the elimination method because my variables are lined up vertically, and I see that I have a positive in front of my x and a negative, and it's going to be easy to make those cancel out. To get it so my x variables cancel out, I have to multiply the first equation by 2. So we get 6x plus 4y equals 10. And now we have the second equation, negative 6x minus 4y equal to 10. Now using the elimination method, we would add these two equations together. On the left side, all of our terms cancel out, so we're left with 0 equal to 20, which we know is not a true statement. So when we get a number equal to a different number, some statement that is not true, that implies there is no real solution to the system. When there is no real solution to the system, that implies the graphs must be parallel to each other. They will never intersect. In this example, we want to solve the system using whichever method. Again, we see our variables are lined up vertically, so using the elimination method is probably going to be easiest. This time I'm going to choose to multiply the first equation by negative 3, which gets us negative 9x minus 18y equal to 30. The second equation, 9x plus 18y equal to negative 30. Now if we add those two equations together, the left side we end up with 0, and the right side we end up with 0 as well. So we get 0 equals 0, a true statement, which implies that there are going to be infinitely many solutions to this system. If we have infinitely many solutions, that means our graphs would coincide, which simply means they lie on top of each other. We could not distinguish one from the other. They're exactly the same graph. The last example is going to be an application problem. Johnson Manufacturing has determined that production and price of a new basketball shoe, similar to Mr. Johnson's classic Adidas Superstars, should be geared to the equilibrium point for this system of equations. So we have our demand equation, which is P equals 160 minus 5x, and we have our supply equation, which is P equals 35 plus 20x. P is going to represent the price of the shoe. X is going to represent the number of shoes sold in millions. On the right, we have a graph that shows what this basic demand and supply curve would look like. What we're looking for is where the supply and demand curve intersect. So the number of shoes that would have to be sold in millions, where the supply and demand was the same, that would also give us the price of the shoe. Since both equations are set equal to P, similar to a problem we did earlier, I can substitute this expression for P into the other equation. Thus we get 35 plus 20x equals 160 minus 5x. Now we just have to solve for the variable x. So if I would add 5x to the left side and subtract 35 to the other side, we would get 25x equals 125. Now dividing by 25, we get x equals 5. To solve for the value of p, we can plug x equals 5 into either of these equations. I plugged it into the first equation, so we get p equals 160 minus 5 times 5, which gets us 135. So the solution to the system would be the ordered pair 5, 135. That's where these two graphs would intersect, which in terms of our problem means there would have to be 5 million pairs of shoes sold at a price of $135. That is the equilibrium point for the supply and demand curve.